Hello and welcome to this video on waves. Specifically today we're going to be talking about harmonics once again and resonance. When we talked about harmonics last, we talked about how they were standing wave patterns. But what we didn't talk about is how they are the natural vibrational patterns. Consider a guitar for a second. If you take and pluck the string, it starts vibrating, it starts moving. And the frequency in which it vibrates is dependent on the length of the string and is known as its first harmonic. In other words, when I pluck at the string, I get a standing wave pattern like so. And by changing where I position my fingers on the string, by changing the length of the string, I change the frequency because the wavelength is also changing. Now, you might get the first harmonic, or the second harmonic, or even possibly the third. But in each case, it is the natural vibrating frequency of the string based on its wave speed and the fact that stimulation is added to it. For instance, if the string here is 0.8 meters long, 80 centimeters, and it vibrates in the first harmonic, well, we can calculate what the frequency it will vibrate at is. First harmonic is like so. It has a length of 0.8 meters, but that is not the wavelength. The wavelength of a standing wave equals 2 times the length divided by the harmonic. Some of you saw this and figured it out via the lab, but here it is calculation-wise. So the first harmonic would have a wavelength of 2 times 0.8 over 1, or 1.6 meters. If I take this and use it with my wave equation, wavelength times frequency equals v, I can solve for what frequency the string will vibrate at. And I'll get a frequency of 265.625 hertz. Just about middle C. This pattern will carry on elsewhere. If I shorten the string by putting my finger here, the frequency will change because the length has changed, which will change the natural wavelength, which will change the frequency it vibrates at, which is how you get different notes. If instead it was vibrating at the second harmonic, however, I would have to go through my calculations again, and I'll get a wavelength of 0.8, which, when I take it over here, would give me a frequency double what I had originally, 531.25 hertz. And this process of natural vibrations, that when you give something a little bit of energy, a pluck, and it naturally vibrates at a frequency being its harmonic, is a very useful topic because it's how most instruments work. It's how guitars, violins, and even flutes, we'll talk more about that later, but it's how we make instruments work. It's how we make music. What happens is instead of vibrating something at its natural frequency, we instead force it to go at a frequency. The idea of resonance is a physics concept where an outside force matches or applies the resonant frequency of an object to it. This is in essence what people did during the Slinky lab when we were looking at standing waves. By manually providing the frequency to the Slinky, you got very large disturbances. You get very large waves. The typical phrasing for this is that the amplitude of the wave was maximized. One of the best analogies I have for resonance is a swing. If you think about a swing as an object going through its natural motion, its natural harmonic, and you push on it at the exact right moment, suddenly the amplitude gets larger. Adding force, pushing on it, adding energy at the exact moment it's swinging will make the person go higher and higher. This is how resonance works. It keeps adding energy at the perfect moment in line with the natural frequency, the harmonic frequency. On the other hand, if you do it at the wrong time, you start hurting your hand, they start slowing down, it's bad. It doesn't increase anything. It shows that the amount and timing you have to push has to be perfect resonance truly works. Now, this is very interesting and causes large vibrations. The most common party trick you see with this is someone breaking a glass using their voice. By giving the natural frequency of the glass, by matching the natural frequency of the glass, it causes it to start vibrating at amplitudes that cause the glass to break. A more historical example, however, is the Tacoma Narrows Bridge. Tacoma Narrows Bridge was a early construction project in the US, expansion to infrastructure. And when the wind blew through the bridge, due to the difference in pressure between the top and bottom of the bridge, it caused a force to start vibrating the bridge. The bridge started shaking up and down. And as it shook up and down, driven by this outside force, this resonant force, eventually it started to break apart, collapsing. There are numerous videos, documentaries of when this happened. Mythbusters even did a episode on a device that's all about trying to match the resonant frequency of something to cause it to shake apart. The idea of a harmonic being potentially beautiful in the terms of music and sound, or dangerous in the term of the Tacoma Narrows Bridge, or other construction projects, is a thing that we do need to keep in mind. Concert halls, in particular, have to be constructed in such a way that the natural frequency doesn't match with any common notes, lest the orchestra literally shake the building apart. Anyways, thanks for watching. Have a good day.